properties of planes, okay? And so this is just sort of like in a way, it's an extension. The textbook takes these two sections and sort of separates them. It does equations of planes and properties of planes. In reality, it really kind of just should be a single section. But hey, we're breaking it into two sections here. So what it does is it just takes that vector equation and the scalar equation, which we learned in the previous section, and sort of starts to play around with them a little bit. So that way you guys as the students can begin to develop like, a feel of how the equations work and things like that, right? So for example, determine the angle between two planes. Well, what I'm going to do is I'm going to draw this out a little bit. Let's say I've got a plane here, right? And then in through this way, I've got, another plane here that comes, oh, that was a bad drawing, like this, right? Hopefully I can fix this like that, right? And I guess that should be erased. And it should be more like this, like that, like that. There. Two planes, and they intersect each other. And they intersect each other at a particular angle. And that angle, basically, if I zoom in, can be kind of found between sort of here and here, right? So you might say, well, how do I find that angle? Well, as it turns out, there's a little bit of an exploit that we can do. This plane here has a normal vector, okay? And as it turns out, this plane here also has a normal vector as well. And it turns out that the angle at which the two normals intersect is equivalent to the angle at which the two planes intersect. And so, in order to determine the angle between the two planes, you just determine the angle between their two normals. And so, you toss them into the angle between two vectors formula. So the angle between two planes is the cosine inverse of the normal for one plane, which I'll call normal 1, dotted with the normal of the second plane, which I'll call normal 2, over the magnitude of normal 1 times the magnitude of normal 2, right? Well, it's not the magnitude formula. I want to write it like this. Magnitude of normal 1 times the magnitude of normal 2, okay? And that would be our angle between two planes. Remembering that normal 1 is the A, B, C vector for plane 1. So I'll call that A1, B1, C1. And normal 2 is the A, B, C vector for the second plane. Okay? And that's what we have there, right? So that's what your ABC variables do, right? Now, this is a question here that I added on a couple years back. It's not really in the textbook or anything. It just sort of came up one day in class. And it says, what effect does changing the constant term in the scalar form of the planar, of the equation of the plane, of the planar equation do? Okay, so that worked. So basically, remember, we've got the constant term. The constant term is d, right? So you got ax plus by plus cz plus this d equals 0. Well, what happens if I sort of increase this d or I decrease this d? Like, what does it do in reality, right? Well, I'll explain here in a picture, okay? So I've got my plane here. Let's say we've got our plane. And the ABC vector is here, right? It's the normal vector, which I'm going to often refer to as just n. Okay, remember, it's the ABC vector, right? Now, if I change this d value, what ends up happening is it's like a vertical shift. It actually shifts the uh, uh, plane, okay, in the direction of, so like the entire plane would get pushed up in the direction of the d of the normal, okay, and then likewise if I decrease it, it would look, move the plane in this direction here, okay. Now I'm not that's not to say that a decrease would always lower the plane and an increase would always uh, uh, make the plane higher, okay. What it does is an increase in this value pushes it in the direction of the normal, and a decrease of the d value pushes it in the opposite direction of the normal, okay. So therefore, if you change the direction of the normal and you use this as your direction, then obviously your d value would also be different, and so therefore it would correspond accordingly, okay. That's what the d value is there for. It kind of like gives your plane sort of a location in space, right? And then changing that would change that location in space, but it wouldn't change the tilt. All right. The only way to change the tilt of the plane is to actually change the A, B, or C values, all right? Or all three, or just two. So I'm going to take a plane, consider the plane that contains the following 3 points. So I don't have any points here. I'm going to make up some points. I'm going to do 0, 1, 2, and let's go with B of 3, 1, 4, and let's go with C of -1, -2, and 0. Okay, here we have it, a couple of points, and I want to find two vectors that are parallel to this plane. This plane contains these 3 points. So here it is. It's got like an A, a B, and a C, and we've got it. There it is. There's our plane, okay? So I want two vectors that are parallel to it. Well, the AC vector would be parallel, and the AB vector would be parallel to it. So a quick and easy way of answering this question would just be to build the AB vector, which, as you know, is equal to 3 minus 0, 1 minus 1, and 4 minus 2, right? And so I'm getting basically a 3, a 0, and a 2. So it's going to be 3, 0, 2 is the AB vector. And then the AC vector would be -1 minus 0, or -1. Then -2 minus 1 would be -3. And then 0 minus 2 would be -2. So that was a -1, -3, and -2, if I remember that correctly. All right. And so there we have it. Those are two vectors that are parallel to the plane. Okay. B, build two vectors that are perpendicular to this plane. Okay. Well, two vectors that are perpendicular to this plane would be one, the normal vector. Okay. And then the other one would be the normal vector sticking out the other side. Okay. So you can kind of see that I've got, that. Well, how do I determine a normal vector? Basically, if I cross product AB with AC, I've developed the normal. So first of all, basically what I'm going to do is I'm going to develop the normal of the plane. So I'm going to cross product. It's XYZ, XYZ, and I'm going to take 302, 302, -1, -3, -2, -1, -3, -2, okay? And then to get my x component, it's 0 plus minus 3 times 2, or 6 here. You see this is a 6. So my normal vector is going to be 6. And the y component is going to be 2 minus 1, 2 times a -1 minus a -6, which is this one, right? And so it's going to be -2 plus 6, I'm getting a 4 there, if I'm doing that right. And then to get, again, my z component, it's 3 times -3. So I'm looking at a -9 minus the 0 here. So a -9, -9. This is perpendicular to the plane. I know because I used the two parallel vectors to create it. And if I want to create two vectors that are perpendicular to the plane, I can actually just turn this vector around by changing the sign of all of its components. There you have it. Oh, I shouldn't write an equal sign there because they're not equal. But I've got normal to the plane, all right? And I can call this normal B, I guess. I'll call this normal A. Okay, so I've got two vectors that are normal to the plane. One is facing in this direction, and the other one would be facing sort of back in that direction. That's B. Let's move on to part C here. Write a vector equation of the plane. Well, this is going to be pretty easy. We already did this. It's x, y, z, right? And I'm going to take a point on the plane, which is going to be 0, 1, 2. That's going to be my r vector, RO vector, plus t. I need a parameter, right? And I'm going to take a slope of the plane, which is going to be 3, 0, 2, plus another parameter. I'm going to use m because I don't like s's. And I need now another slope. Another slope is going to be -1, -3, -2. All right? And so there's that, okay? Let me erase some of these stray marks. Okay, bang. I've created a vector equation to the plane, right? Create a scalar equation to the plane. So this is D, right? Remember, the scalar equation of the plane requires the normal. And so it's basically just 6x plus 4y plus 9z. It's actually minus 9z. Plus d equals 0, right? But now I just need a point. Well, a point on the plane is 0, 1, 2, point A up here, okay? So I'm going to go ahead and place a 0, a 1, and a 2 there, and that'll allow me to solve for my d value. And so I'm going to get 6 times 0 plus 4 times 1 minus 9 times 2 plus this mystical d value, which we're about ready to find, is going to give me the d value, all right? It's going to give me an equation that allows me to find the d value. So looks like I've got 0 plus 4 minus 9. 9 times 2, though, 18. 18 and 4 is 14, negative, so I'm getting d is 14, all right? Hopefully I did that right. And so there we have it. My equation in scalar form is 4y minus d, minus 9z plus 14 equals 0. Okay? These two equations, here and here, are the same plane. This one is written with a certain set of definitions, and this one is written with a certain set of definitions called vector form and scalar form, okay? Determine if this point is on the plane. I feel like we've done this whole stuff already. So basically one of the, for part E, I'm going to see if a point's on the plane. I'm obviously going to use the vector form, and so I'm going to use 6 times 9 plus 2, plus 4 times 2. 4 times 2 minus 9 times 5 plus 14 equals 0. Does this equal 0? I doubt it, because remember, I just pulled random points from the sky, and this was another point that's also randomly pulled from the sky. Now, is that on the plane? I think one year I actually got a point that was on the plane that I made in the notes in class, and it was a spectacular event. It went down in history. Let's see if I did it this time. I doubt it. It looks like I did not do it this time. Shoot, I might be close though. 6 times 9, and this is 5 times 9 over here. And the difference between those is 9. So what's 9 plus 8? Oh, so close. 9 plus 8 is 17. Oh, no, plus 14. 17 plus 14. I was thinking it was minus 14, and I was going to get up with a 3, but I didn't. Whatever the case, it's not equal to 0. And so, as we've discovered that this point D is 9, 2, 5, it is not on the plane. Not on the plane. Okay? Okay, part F. Write a vector equation of the line that intersects the x and the z intercepts of the plane. Okay, so this is F. All right, so I'm going to go ahead and draw this. So I've got my plane here, and I would like to focus on the x-intercept and the z-intercept. Okay, so imagine I've got like some kind of plane that's sort of flying through the air here, and it kind of goes like this, and all of this, it sort of intersects these two locations. This is under the axis, all right? It intersects here and here. The answer, this question is asking us to build a line that goes through these two intercepts. Okay? So, well, first thing what we need is we need the x-intercept. Well, remember that the x-intercept is x, 0, 0. The z-intercept is 0, 0, z, right? Okay? And for our plane, it's going to be 14 over 6. So this is going to be 14 over 6, 0, 0. And this is going to be 0, 0, 14 over negative 9. Let's go see that last video, because remember, basically, in order to find an x-intercept, I take the d value, pass it over, and divide by 6, because both of these become 0. And likewise, to find the z-intercept, these become 0, so you get rid of that stuff. And you're looking at negative 9z plus 14. Well, you subtract 14 and you divide by 9. Oh, I forgot to make these guys negative, right? So that's negative, and that should also be negative. Okay, so there we have it. We've got now 2 points, which I guess I'll call this guy point X, and I'll call this guy point Z. All right, so point X and point Z. Now I got to build a line. Oh my, I got to build a line that's X, Y, Z that goes through those 2 points. Well, remember, let's go back to a line. The line needs a point and a slope and a parameter. I've already used the parameter t in this question, so I'm going to use a different parameter. I'm going to call that p, for example. Now I need a point on the line. Well, I'm going to use 0, 0, negative 14 over 9, positive 14 over 9, because I'm going to reduce that fraction. So there is my point on the line. Now I just need a slope. Well, the slope could be the vector zx, for example, or xz for that matter. It doesn't matter. I'm going to make xz just to go in alphabetical order. So it's basically, how do I make vector xz? Well, I take the coordinates for point z and subtract each one of these. So it's that minus that. Okay, so 0 minus a negative 14 over 6. Well, that's simply a 14 over 6, comma, what's 0 minus 0? Well, that's 0. And what's 14 over 9 minus 0 is simply just 14 over 9. And there you have it. This line intersects the z-intercept and the x-intercept of the plane. Okay? And we built it. That's pretty cool. So again, we ended up using the scalar form there. Much easier to use. So that was just some random questions that you'd be asked. Take a look at some of that stuff there.